All right, let's get started. Hi, everyone. Welcome to the MIT Mobility Forum, organized by the MIT Mobility Initiative. I'm Jinghua Zhao, Professor of Cities Transportation at MIT. Today, I'm really excited to have Professor Pat Mokhtarian join us, talk about the insidious problem of selection bias and how to recognize them and how to do what to do about them. Right? As you may heard at the beginning of the chit chat, many of the audience here, including myself, a grown-up researcher reading Professor Pat Mokhtarian's paper, so I'm really honored to have her join us today. About the topic of selection bias, right? It may sound a little bit technical, but I think most of us have quite a bit of sense, intuition here. Let me give Professor Fred Manning was here. I'm quoting his example, mentioning about motorcycling during the rainy day. Is this because rain makes the motorcycle more dangerous? Or only because the most adventurous and risky motorcycle come out during the rainy day, right? So that's one example of such selection bias. Yeah. The other thing I think often cited is actually the higher education system as a whole. See, I mean, many students want to come to MIT, this MIT forum, but when we say MIT alum are very successful, are we saying we actually enlighten them, train them well? Or we just selected the best student to start with, right? So MIT merely a filtering mechanism. So that's another example of this selection bias. The second thing I wanted to mention before I formally introduce Pat is that many people may also have a sense that, oh, we know what selection bias, but it just kind of play at the margin, small magnitude impact. That's actually could be very wrong. I mean, ignore selection bias, we may make categorically wrong decisions or directionally wrong on this, right? So today, there's no better person than Professor Pat Mokhtarian to really talk about this issue and to talk both in a kind of intuitive sense and also a partly technical sense here. We only have 1 hour, we cannot get to too deep of mathematics, but I need to introduce some degree of technicality. Right. So as a warm-up, I invite everybody in the chat to type in your organization, your local, your location and the time. So that gives Pat some background who the audience are. So I would say MIT, Cambridge, 12 notes. Right. So I invite everyone to type into the thing. Thank you. Yeah. While we're doing this, let me restate the norm of the form, which is we invite everybody to contribute one idea, either in the form of a question to Pat or a comment to the presentation here, right? For example, in this setting, you can say, oh, there's a phenomenon observed in my life. I suspect there's some selection bias going on here, right? A prompt like that would be really helpful. Yes. All right, so Pat Mokhtarian is the Clifford and William Grant Jr. Professor in the School of Civil and Environmental Engineering at Georgia Tech. Before that, she worked at the University of California, Davis for many years, where she is a professor of civil and environmental engineer, associate director of the Institute of Transportation Studies, and a founding chair for the interdisciplinary master and PhD program in transportation technology and policy. Her research really look at, I put there 3 things. One is the impact of land use on travel behavior, particularly include the residential location and residential self-selection bias is one such example. Second one is the impact of the telecommunication technology on travel behavior. Today, we've been talking about remote work quite significantly, but Pat started the study a long time ago, really the founder of this type of a research stream. The third one is Pat challenged the classical notion of transportation is merely a derived demand. Meaning that travel itself isn't useless, so all we need is to get to the destination. She actually offered a tripartite interpretation of travel utility. There's the destination utility, as typically know, but also introduce the need to travel for its own sake, and also multitasking and utility during travel as a third component of the travel utility. Yeah, she's the editor of the journal Transportation and on the editorial board for many journals like TR Part A, Transportation Policy, Transportation Letters, etc. Here, Professor Pat has been named the 2021 recipient of the Lifetime Achievement Award from the International Association for Travel Behavior Research. Pat is actually the first woman recipient of this prestigious award. And also, I learned just this year, Pat is elected to the National Academy of Engineering. Right. Without further ado, let me pass the forum to Professor Mokhtarian. Pat, please.
Great. Thank you so much, Jinhua, and thank you all for coming. It's really a pleasure and an honor to be part of this. And so I'm looking forward to our discussion. I realize that we do have a large spectrum of, knowledge about selection issues in this audience. So I hope there'll be something for everyone, but I'm keenly aware that some of you probably know this subject even better than I do. So I am certainly still learning myself, but have come, a long way, thanks in large part to a couple of my brilliant PhD students, which I'll be mentioning as we go along. So without further ado, I want to get into it because there is a lot to say on the subject, and it's a struggle to boil it down to some of the essentials. So loosely, the talk will be following the topics as listed here. We'll start with an introduction, give some basic concepts that will give us the foundation for what comes next, which will be a partly intuitive and partly technical explanation of the selection bias problem. And then the solution that I'll be focusing on today is endogenous switching regression models. There are other types of models in similar family and also different approaches to selection biases, but this is the one that I'll focus on now. And as Jinhua mentioned, yes.
Sorry to interrupt. We don't see your slides there yet.
Oh, that's a problem. Why do you not? Because screen one is screen one. I thought, I always forget to click share. Thank you.
Got it. That's great.
Okay, that's one last click. All right. So yes, all these topics that I've just been mentioning, and then we will get to the conclusions, of course, because every talk has to conclude. So let's keep going. What are we talking about in our particular scenario? And again, there can be other scenarios under which we have a selection bias, but I want in this talk to kind of alert you to some generic ingredients for which we should be on the lookout for a selection bias. So the scenario I'll be dealing with is one in which we have a discrete event which is of keen interest to us, and we'll call that event a treatment or an experiment or an intervention. What do I mean by that? It could be an extreme event such as an earthquake or a bridge collapse, or it could be adoption of a new technology, whether medicine, agriculture, telecom, or whatever, or it could be a policy and a newly passed law or regulation, such as something dealing with transportation safety and so forth. And we're also going to assume that all individuals will either be treated or untreated. Now, in a variation that I'll be dealing with in the application, there can be multiple kinds of treatments, either ordered degrees of treatment or categorical treatments, but everyone will be either untreated altogether or treated in some way. And based on the kind of scenario that might be in play, individuals may be actively choosing to be treated or not, or they may just be passively experiencing the treatment, as in the case of an earthquake or perhaps a law being passed. So our mission as analysts or policy makers and policy analysts is to estimate the effect of this event of interest on an outcome of interest. So we'll be estimating what we call the treatment effect. Now, what kinds of outcomes might we be interested in? If we're talking about medicine, the outcome might be blood pressure. If we're talking about agriculture, it could be crop yield. If we're talking about transportation, it could be vehicle miles driven or any of a number of other travel behavior or transportation outcomes of interest. So we will also, again, for this type of approach that I'll be dealing with today, be assuming that we're going to observe the outcome, whether a person is treated or not. For example, if we're talking about vehicle miles driven and the treatment is teleworking, we'll observe someone's vehicle miles driven, whether they telework or not. Whereas in some kinds of scenarios, you might not even observe the outcome unless the person is treated. But in this case, we'll be observing the outcome either way. So just again, to give a few more transportation examples, a treatment might be wearing a helmet while cycling or while motorcycling. The outcome of interest might be injury severity. Or we could talk about several other options like buying a fuel-efficient car, living in a transit-friendly mixed-use neighborhood, or adopting teleworking, as we'll see later, in which the outcomes of interest might be something like greenhouse gas emissions, vehicle miles driven, and so forth. So hopefully that's giving you some ideas, sparking some ideas of situations you might encounter that fit this scenario of interest. So what treatment effects, and we'll abbreviate it TE in later slides, might we be interested in? Well, actually, there are three different kinds of treatment effects. The first one is the treatment effect on the treated. And by that, we simply mean what's the difference in the outcome of interest between for a particular person and then averaged over the people who are treated. What's the difference in the outcome if they're treated versus if they're not treated? But again, we're only looking at that over people who have been treated. So you might use this measure of treatment effect if you're interested in documenting what's been the impact so far or the effect so far of this treatment, intervention, experiment, law, whatever. But we might also be interested in the treatment effect on the untreated, meaning kind of looking forward, what would happen if people who are currently not treated become treated. And that, of course, then would be the difference between the outcome if someone is treated versus if they're not treated for those who have not yet been treated. So how would the outcome be different or have been different if they were to be treated or if they had been treated? And then we might be interested in the average treatment effect overall, which, as the name suggests, is going to fall somewhere in between the treatment effect on the treated and the treatment effect on the untreated. And that's going to be the average impact of treatment for a randomly selected person from the population, which, of course, will contain both treated and untreated individuals. So these may seem conceptually quite different to you, and in fact they are, but what surprised me as I was looking at the literature a while back was that a number of papers don't even say which treatment effect they're dealing with. They'll talk about a treatment effect, and when you read more closely, you thought it was the average treatment effect, but when you look closely, it seems like it was the treatment effect on the treated. So it's not always even clear which effect the authors are intending to analyze or present. So that's one source of confusion for the novice to the literature, I will tell you from experience. But in any case, we have these three options. So you might be saying, well, how hard can it be to estimate a treatment effect? Well, here's why we have a problem. If you remember on the previous slide, I kept saying the difference in the outcome between the treated case and the untreated case. Well, the trouble is we only observe people in one of those situations or the other. So we only observe the treated people in their treated state. We don't observe them before they got treated, and conversely for the untreated individuals. So we refer to this other state that we don't observe them in as the counterfactual state, the what would have happened otherwise kind of state. So you may say, well, I get that, but can't we just model an outcome like this? Y being our outcome variable, and let's just say linear regression for simplicity. And we've got a vector of explanatory variables, x's, and a vector of corresponding coefficients, betas. And then we've got a t variable, which is just a single variable, a dummy variable, which is equal to 1 if the person is treated or not, with a coefficient delta. And this equation applies to each individual, but throughout I'm going to omit the individual level subscripts for simplicity. So you say to yourself, well, when I estimate the parameters of this equation, the betas and the delta, isn't delta hat our estimated coefficient of the treatment effect? Of the treatment dummy, I should say, wouldn't that be the estimated treatment effect? And, on the surface, it seems like it, but, the immediate question is, which of those three that I mentioned is it? After all, you can't really, with this equation, differentiate among those three kinds of effects. So in essence, with just a single equation like this, you'd be forcing all three of those effects to be equal, which doesn't seem very satisfactory since in real life they may well not be. So you say, okay, I get that. Why don't we then do separate equations for the treated and the untreated? So let's just have a y outcome variable if treated and have that be a function of some x variables, but with coefficients beta that are allowed to differ from the same equation for the untreated people. And if we do that, then we think we could get the average treatment effect as the average over the entire sample of y hat t minus y hat u, where admittedly the y hat t equation is only estimated for the treated and the y hat u equation is only estimated for the untreated. But still, we'll have those coefficients for each group and we'll have everybody's x's. So in principle, we could compute this effect and call it the average treatment effect. Well, and we could also get the other two treatment effects by looking at the average only over treated people of the same difference, where in this case, we're applying the beta hat u coefficients to the treated people's x's to get their counterfactual, so to speak. And in the next line, to get the average treatment effect on the untreated, we're applying the beta hat t's to the untreated people's x's to get the counterfactual y hat t if the untreated had been treated. So that all looks well and good on paper or on the screen, as the case may be, but it's still a problem. It would not be a problem if, in fact, the treatment were randomly assigned across the population. Then if everybody's randomly getting either treated or untreated, and we've got a large enough sample and it's representative of the population, then the sample we draw from each of the two groups separately, treated and untreated, because we're still only observing them in one state or another, but each of those samples would be random samples from the population of interest and the population of overall population of outcomes. But here's the rub, here's the heart of our selection bias problem. What if the treatment is not randomly assigned? And you can stop and think about some of those examples that I gave earlier, and I'll come back to, making that more tangible in a moment. But the key issue is, what if the treated group differs from the untreated group in ways that are relevant to the outcome? In that case, we're going to have a selection bias. Again, here's our examples. What if the people receiving the new medical treatment are sicker to start with? What if the farmers trying the new fertilizer are just, willing to try new innovations of a bunch of different kinds? What if the people wearing a helmet before they had to are either safer in general to start with, or maybe, they voluntarily wear a helmet so that they can engage in riskier behavior and still feel like they'll be okay, protected. Or what if those buying a fuel efficient car want to travel more in the first place, but you're trying to measure the effect on vehicle miles driven of owning a fuel efficient car. So I think you can see that that could be a problem for getting an unbiased estimate of our treatment effect. And it's especially likely to happen when the individual voluntarily adopts the treatment, because after all, they may have an agenda, a reason why they would be more inclined to adopt the treatment than others. But it can even happen in the case of an involuntarily imposed treatment, such as an earthquake. Earthquakes don't affect everybody in a region equally, and so forth. So here's the heart of our problem. And let's, again, drill down a little bit deeper. If the to be treated people before they are treated already differ from those who are going to remain untreated, then our problem is, how can we separate the effect of the treatment from the effect of those pre-existing differences between the treated and the untreated groups? Well, some of those we can separate the effect if the differences are due to observed characteristics, the x's that are in our model. Then we are accounting for those. But what we're worried about are unobserved differences between the two groups of treated and untreated people. And those are going to be in the EDAs, the error terms of our models of the outcome that we saw on the previous slide. So the moral of the story is, we should not expect the treatment to have the same effect if it were imposed on or adopted by a currently untreated person, if those treated people already differ from the untreated even before the treatment occurs. And you may think, well, can't I still at least estimate the treatment effect on the treated using the kinds of equations I showed on the previous slides? And the answer is no, sadly not. So the naive approach of just doing a regression equation on each group separately and then, doing those y hats isn't going to get us there, because our estimated treatment effect on the treated is going to confound the true effect of the treatment with those effects that are due to pre-existing inclinations or traits that may have caused a portion of the observed effect to occur even without the treatment. And that's Jinhua's example of people benefiting from an MIT education. You know, how much of that benefit was due to the MIT education as opposed to being smart and well prepared and motivated, etc., even before they went to MIT. And so it's very hard to tease out what's due to those the differences in predisposition or pre-treatment inclinations or traits from those that are actual effects of the treatment itself. So what it boils down to mathematically is our estimates of those coefficients that we're using to compute the average treatment effect are going to be biased by virtue of being based on non-random samples. And we can talk now a little bit of more equations just to give us a bit of foundation for what's to come. For those who are just learning about this, I can mention that we have two components to our model system. And by model system, I'm referring to the endogenous switching regression model, the ESRM for short. It has a bunch of different names in the literature, which is one signal that it's been around for quite a while. So this is not my invention or the invention of my students and I by any means. It's been around for decades. But we have the two components. The first one is the selection model, which in our context will be a binary probit model. And that's a model that governs selection into treatment. So our equation will give us, explanatory variables explaining selection into treatment, associated coefficients, and the person will be treated if the Z star, which is unobserved, but a latent index of propensity to be treated, they'll be treated if that Z star is greater than 0 and untreated if it's less than or equal to 0. And notice we've got an error term epsilon associated with the treatment model. Selection model, excuse me. And then we've got an outcome model for each of our two groups. And I'm just right now giving you kind of the standard binary case where we've only got two groups, treated and untreated. In the application, I'll show you shortly, if I don't run out of time, we'll have two treated groups and still an untreated group. So we'll actually have three outcome models. But for now, the classic original case was just two groups, treated and untreated. And so those equations look just like what we've already seen. Our error terms there are etas. And then we make assumptions on the error terms, specifically that they're all normally distributed. So we've got a trivariate normal distribution with means equal to 0, as we'd customarily assume for regressions and for discrete choice model kinds of things. And then our variance covariance matrix of our three error terms. We'll just focus on the covariances between the epsilons and each of the etas and point out now that we've got a row term, which is a correlation of unobserved characteristics that both influence the selection into being treated or untreated and also influence the outcome. So this pesky little row J here is going to be the source of our selection bias. And one of my students, Sung-Hoo Kim, so I've got the reference down here, really illustrated this in a lovely fashion, I would say. So I'm borrowing from our paper to use this illustration. The problem is that the distribution of our epsilon, the error term of the selection model, is truncated for each subsample because we're only observing from a portion of that distribution of epsilon for each group. But if they're uncorrelated, if the epsilon and the eta are uncorrelated, that truncation of epsilon doesn't matter. So here's the situation where we're plotting the joint distribution of epsilon on the horizontal axis and our eta for the treatment equation on the vertical axis and for the untreated equation over here. Oops, sorry. And you can see the truncation on epsilon for the treated group where epsilon's greater than 0. We're only sampling from this half of the, epsilon distribution shown over here. So it's truncated, which of course will move the mean of the epsilon distribution away from 0. So the heavy dashed line is the conditional mean after truncation. But notice if the epsilon and the eta are not correlated, it doesn't do anything to the mean of the eta term. So when epsilon and eta are uncorrelated, the selection bias doesn't exist. It basically, we can still sustain the assumption that the expected value of our eta terms is equal to 0. But if the eta is correlated with epsilon, that's when we have the problem. And here I'm just showing a positive correlation, but it works also, of course, with a negative correlation. And so the thing is that we're still sampling from a truncated distribution for epsilon. And now because of the correlation between epsilon and eta, we're not only moving the mean for the epsilon distribution, we're also moving the mean for the eta distribution. Sorry, I keep clicking inadvertently. And so we're no longer can assume that we've got a 0 mean for the eta term. And that's the problem, because if we estimate an ordinary regression without correcting for this shift in the mean, the bias in the mean of eta, then we're absorbing that bias into our estimate of the coefficients of the betas in our outcome equation, and therefore getting, just face it, wrong estimates of the coefficients. So hopefully, I know I have to speed on, so I know that went pretty quickly, but again, I'm happy to share the slides with anybody and hope that you'll at least get the basic idea here. So just to kind of reiterate what I've said in English, I think I'll have to skip that in the interest of time. But again, basically, it boils down to that correlation of unobserved characteristics influencing both selection into being treated or untreated, and also influencing the outcome. So what's the solution? That's the problem. Do we have a solution? Yes. Fortunately, the endogenous switching regression model knows what the selectivity bias is and corrects for it, which produces unbiased estimates of the model parameters and thus the treatment effect. So here's what we really want. We want the conditional, that is the population-wide averages of our outcome, Y. But what we get instead are the conditional expectations. So we're getting the expected value of Y for of treatment, associated with treatment for a treated person, where this expected value of our conditional error term is not 0, but equal to this. And this is the so-called inverse Mills ratio term in purple, but this whole term is a function, as you might guess, of the covariance or the correlation rho, in this case, between epsilon and eta. And it's also a function of the probability of being treated. And similarly for the conditional expectations for the untreated. And then the beauty of this is that we also get counterfactual conditional expectations. So we can see what the expected value of the outcome would be for an untreated person if they were to be treated, and conversely for a treated person before they were treated, or if they were to become untreated, if that's possible. So again, having to hasten on, restating the problem, if we're estimating an equation like this, where we've got a conditional expectation that's not equal to 0, when it really is equal to this term here, the non-zero bias term is going to get absorbed into our X beta term, and that's going to bias our estimates of the betas. So once we account properly for that selection bias, we can get unbiased estimates of our beta T and our beta U, and then compute the treatment effects properly. So again, I would love to linger on this slide, but I will have to hasten on with apologies. So let's get to our applications. We want to look at impact of working from home on vehicle miles driven, and I have to give, of course, all the credit to my PhD student, now Jinhua's postdoc, Jenny Wang, whose dissertation has already won a couple of awards, and very proud of what she's done with this. Just some acronyms that we'll be seeing throughout the rest of the talk: work from home, telework, For the purposes of this talk, we'll treat those two as equivalent, teleworking and working from home. I know there are differences. I've written papers on defining teleworking, but for the purposes of this talk, we'll treat them synonymously. And then we've got three categories of workers, as I mentioned briefly earlier. We've got non-teleworkers. We've got what we call non-usual teleworkers who work from home greater than 0, but less than 3 days a week. And we've got usual teleworkers who work from home 3 or more days a week. And our outcome variable of interest is vehicle miles driven, or VMD. So can't linger on this slide either, but the upshot is when you think about transportation impacts of working from home, especially on vehicle travel in particular, some impacts can reduce travel, some can increase travel. So what will the net impact be? And the answer is we don't really quite know. But what Jenny and I noticed when we were looking at the literature on transportation impacts of teleworking, and I can attest personally, and other people on the call have also been involved in some of these studies that go back to the 1980s, we found this very sharp divide between what the studies on the left were finding in terms of directionality of impact, as Jinhua was saying, and what the studies on the right were finding. The studies on the left were the early studies. They tended to find travel reductions, that teleworking decreased travel, whereas the later studies on the right tended to find that teleworking increased travel. And what was interesting was that the early studies tended to be panel data, longitudinal data, measuring people actually before they started teleworking and after they started teleworking with control groups. Whereas the studies finding complementarity tended to be cross-sectional only. And so to see how both of those results could occur, we thought that this schematic might be useful. And I think it pretty aptly illustrates the difference between having longitudinal data and having only cross-sectional data. Suppose we have two groups of people. The purple are the people who adopt teleworking at some point in time. The orange are the people who do not, the non-teleworkers. So we measure everybody at time 1 after some have adopted teleworking and others have not. And so our cross-sectional impact, if we measure everybody at just the one period of time, our cross-sectional impact is here. And we see on average teleworkers travel more than non-teleworkers. So we say, teleworking seems to increase travel. And I put increase in quotes because all we really see from here is that teleworkers tend to travel more than non-teleworkers. But if we could have observed our teleworkers before they started teleworking, which is what we do in a longitudinal study, before and after study, we might have noticed that they traveled even more before they started teleworking than they did after. And therefore that in longitudinal terms, comparing their before and after travel behavior, they actually reduced their travel. So they reduced their travel from way above average to above average, but still above average. And so it looks like they increased their travel if you're only comparing cross-sectionally. So what's the problem is that with only cross-sectional data, we're missing this important counterfactual over here. And that's exactly what the endogenous switching regression model gives us. So we'll also get the counterfactual for what would happen if a non-teleworker started to telework. So we'll have all of those things, as I mentioned. So this is clearly a job for the endogenous switching regression model. I don't have time to dwell again in detail on Jenny's many contributions in her dissertation. So again, I'll just plow ahead in the interest of time. But it's a very rich set of contributions. Again, I won't linger over data collection, but just to say we collected the data that we're analyzing here in the spring of 2021 with samples from Dallas-Fort Worth and the Washington, D.C. metropolitan areas. We're currently doing some more bells and whistles on data that we've collected in 2023. So we'll get a more recent estimate of the treatment effect with work that's in progress. Our sample size is about 1,600. And so we've also weighted the sample very carefully on a whole bunch of variables. so that all of the numerical or empirical results I'll be showing are based on the weighted sample, which is as representative as we can get it of the populations of those two regions. So just to briefly mention the components of our treatment effects, when we've got now 3 groups, 1 untreated and 2 treatment groups, the rows are illustrating the status that we observe them to be in. The columns are their potential statuses, so all 3 are the same statuses. So our diagonal elements of this 3x3 matrix are the factual effects, that is, what we actually observe non-teleworkers VMD to be, what we actually observe non-usual teleworkers VMD to be, and so forth. And all the other elements of this 9-cell matrix here are the counterfactual effects. So for example, this one here, the first row, second column, is the expected vehicle miles driven of a non-teleworker. We observe them to be a non-teleworker if they were to adopt non-usual teleworking and therefore start teleworking less than 3 days a week. So on the next slide, you're going to see these 9 quantities, the averages over the sample/population of these 9 quantities plotted on this graph, but I guess I forgot to show that looking at differences in these different elements will give us the various treatment effects. So here are those 9 quantities for our full sample. And the green are the usual teleworkers, the orange are the non-usual teleworkers, the gray is the non-teleworkers. The horizontal axis is an approximation of teleworking frequency, so not teleworking is 0, and we spaced out the non-usual and usual teleworking proportional to their average frequency of teleworking to give a more realistic picture of the trends between the various groups. The vertical axis is vehicle miles driven per week. And so the circles are the counterfactuals and the triangles are the factuals, the specific counterfactuals associated with not teleworking. So I didn't, show all the counterfactuals with these circles. And you can see then by comparing the factual and the counterfactual estimates, if you look at the orange triangle and the orange circle, hardly any change. The non-usual teleworkers barely reduced their travel. It wasn't even statistically significant. But if you look at the usual teleworkers, then they reduced their travel substantially, comparing the green triangle to the green circle here. So we said, okay, the usual teleworkers outweighed the non-usual ones, at least in 2021. And so overall, it turns out that we had a reduction in travel due to teleworking. But we did one more thing, and that was stratify the sample or split the sample into people who are stressed and those who are not stressed, travel stressed, I should say, on the basis of attitudinal statements. And you can see similar directionality of a pattern, but much stronger decreases in travel for the travel stressed. If you just look at the green here versus the green here, much stronger decreases in travel for both groups, the usual teleworkers and the non-usual teleworkers, for the travel stress compared to the non-travel stress. So moral of that story is, if you're adopting teleworking, probably in part because you're travel stressed and want to reduce your travel, it's going to have a bigger reduction impact on your travel, which makes perfect sense. But it also illustrates that we're mixing different kinds of people in the population who are adopting teleworking for different motives. I'll gloss over this one, except to say that each individual dots here are individual cases in our sample. So this is another example of Virginia's beautiful visualization of our results, so that by looking at this, we can see what share of cases, in this case of non-usual teleworkers, actually increase their vehicle miles driven after adopting non-usual teleworking versus decrease it. So we're focusing on the ones above the line here, are those who travel more vehicle miles driven after adopting teleworking. Among the travel stress, 30% still increase their travel after adopting teleworking. So, it doesn't reduce it for everyone, but on net, for most it does. And a much higher share of non-travel stress, non-usual teleworkers increase their vehicle miles driven. So that's the part of what I'm saying. I'm winding down, honest, Genoa. So empirically, we've identified all these things that in all models, teleworking reduced VMD on average for its adopters. It did so most of all for travel stress teleworkers, and found that they were much more likely to increase vehicle miles driven after beginning to telework, if they were not travel stressed compared to being travel stressed. Methodologically, this is just a reiteration of what we've already talked about, and just the last point comments that I think we can resolve this apparent paradox, if you will, in the literature, with so many studies finding reductions and so many other studies finding increases, by saying the cross-sectional results can be consistent with the longitudinal ones, using these kinds of approaches to tease it out. And finally, just this slide reiterates the generic ingredients of a selection bias. I don't think I need to rehearse that again, but just a reminder then of what the generic question that is raised by these kinds of ingredients up here. That is, could part of the apparent effect of the treatment on the outcome be due to unobserved pre-treatment differences between the treated and the untreated? And if so, then if you don't correct for that bias, don't assume that future treatment or adoption will provide the same results as what you've observed for the already treated. I've got a bunch of other transportation applications here, but again, I'll skip over it so as to, Jin was squirming, I can tell. And this is my last slide, that there are lots of other applications beyond transportation, as you might imagine. So go tell all your friends and neighbors. We very often only have cross-sectional data. So I couldn't resist, since I put Jenny's picture earlier. Sung-Hoo is my other recent PhD student, now a professor at Hanyang University, whose work from his dissertation also sharpened my own thinking and contributed to those visualizations that we saw earlier. So we're hoping that this collection of papers will help spread the word in a way that maybe helps demystify some of pretty technical literature, presented in a way that might be a bit more understandable, and the visualizations and applications should be of interest in their own right. So thank you very much, and I will stop sharing.
Great, thank you so much, Pat. Thank you for both the actual case on the teleworking's impact that medical are looking at, but also the general discussion on the methodology. We have a shorter time. Let me invite Professor Fred Mannering, give a short remark, and also Professor Chandra Bard some remark, and then give it to John for the question audience. I will try to keep my remark shorter on this thing. Fred, please.
Okay, sure. And I just thank you very much for the presentation, Pat. Very good. I just wanted to point out a couple examples to show you how pervasive the sample selection treatment problem is. Going back to my talk a few weeks ago, I mentioned if you have cars with safety features, you just can't look at the cars with safety features and without, because the people that buy the safety featured car are the safest drivers. So there's this sample selection process. And the example I use in my textbook has a route choice problem where you have a freeway, an arterial, and a rural road. And the fastest drivers tend to take the freeway, but you only observe them on one route, right? So again, you have this sample selection problem. And I know this all started, I guess, James Heckman's seminal work in the late 70s, which he shared the Nobel Prize with Dan McFadden in 2000. We've been working on this for decades, and Chandra and his colleagues have carried the ball into the in the future decades. But it becomes sometimes with the highly nonlinear models that we use, the corrections become very difficult. And this is what if you look at what the economics field has done to address this problem, is they've started these causal inference models where they simplify the models, use fixed effects to try to control for the selectivity problem. But it is pervasive, as Pat pointed out, not just in transportation, but almost every field. So I guess my question for Pat is, we've been struggling with selectivity for many decades. How do we, and a lot of people just ignore it, right? That's the easiest thing. So how do we get the word out to keep focusing on the need for this type of correction? So it puts a lot of pressure on Pat, but here you go.
Well, and again, you know, I'm a newbie with respect to giants like yourselves and others. So I guess what I try to do is to be a bridge between the theoreticians or those who can speak in highly technical terms, but don't always, you know, write an article that's readable for people like me and those who are new to this issue. So what I hope to do is to try to be a translator, and so to the extent I can do that, then I'll feel very happy. And all I know is we just keep talking about it. You know, when I review papers, I'm like, what about, you know, these people differed from the others to start with and so forth. So, you know, just much like any thorny problem, I think we just have to keep beating the drum.
Great. Thanks, Fred. Chandra, please.
Yeah, thank you, Pat. Very interesting talk, as always. I saw some comments in the chat. First off, something that I have been pretty passionate about recently also, and I will talk about this at the IATBR meeting. You know, this whole issue of what kind of data, does panel data really do a whole lot in terms of teasing out causality? And I'm becoming more and more convinced that with appropriate rigor, cross-sectional data has so much to offer to tease out causality. Panel data is not a panacea. It's got its own so many different ills. And I'll, you know, make that point very strongly during my talk at IATBR. And Pat, thank you. Give me the slides. I might even borrow a couple for my IATBR talk. A few other things, you know, just to add to Fred Mannering's thing of examples, we completed a paper recently about if I have all of these technological gadgets in our cars, such as lane assist systems, automatic braking systems, what does it do? Does it actually improve safety? And the general idea is, yes, it improves safety, but not as much. And what Fred would characterize as an offsetting effect. What's the offsetting effect over here? Who are the ones who buy these safety gadgets? They are the ones who are generally conservative. They don't try to expose themselves too much. So they drive less to begin with. So if you look at the data without taking the self-selection into account, that those who purchase these technological gadgets in their vehicles are more conservative and typically will drive less. If you don't take that into account, you don't actually see the impact. And what we found after accounting for the self-selection is that people who, if individuals have these gadgets in their cars, they actually drive more. And driving more means, you know, it offsets safety because of exposure. So we did some interesting analysis. So I think part of the idea is really to try to convey. And when I work with my students, I try to tell them, don't dive into the model. We need to give examples. We need to trigger the thoughts of individuals. So that's one thing. The second thing I would say is, you know, this belongs to the very general class of endogenous explanatory variables. All of these models we are talking about, switching, self-selection, and a whole other bunch, they're really endogenous explanatory variable kinds of models. A couple of things, I did put something in the chat. What we are also finding, and this is interesting, is that the distributions of the margins of the error terms and of the dependence term, they seem to impact our effects of how much is self-selection and how much is the causal effect to quite a substantial degree. And you have non-parametrics, you have other ways of doing it. But most recently, in January of this year, I came up with a proposal of very nicely, conveniently, without much estimation difficulty, incorporating some of these non-normalities and very general distributions. So I think these things are evolving over time. So we do have methods. And by the way, as Pat and Fred very well know, this is not just endogenous switching regression. We can use the same concept for endogenous switching, ordered response, endogenous switching count, whatever you want to, any other type of outcome. So let me stop there. A very fertile field and so much more to do over here.
Great, thank you, Chandra. So on this, yeah. So given the time, I think I will just make one remark and just skip my question, pass it to John for the audience question there, which is what Fred mentioned about how do you let this knowledge be known to the broader society there, right? So there's one level which is educate all the PhDs, the graduate student, etc. There's another level which is the public. But let me add another layer, which Professor Cynthia Chen mentioned, is the mission agencies, the DOT, the DOE, the Ministry of Health, etc. Are they aware of these major issues? Therefore, when we make public policy, we're not making blunders in that. That's a critical aspect we should move out to. But without, let me give the time to John for the question from audience. Yeah, please.
If I can just respond to that real quickly.
Oh, sure,
I also teach, at least at a much less theoretical level, but at a instinctual level, this idea of selection bias, and a couple of graduate classes that our master's students would take, and they're the ones that go on to work for the DOTs or the consultants or whatever. I also think in public health it's probably more salient from the standpoint of well aware of issues associated with the gold standard of double-blind experiment. So you do randomly distribute the treatment in many cases in medical trials, and understand selection biases in observational studies much more. But yeah, I think it is the challenge. It starts at not just our PhD students, but even our master students, and maybe even undergrads need in an undergrad probability and statistics course some understanding of. I keep trying to tell mine that if you don't have a random sample, all bets are off with respect to what properties of estimators that we're talking about here. But admittedly, it's hard to get through at that level. They don't experience it yet.
Great, thanks, John. Pat, John, please.
So Pat, just building on Fred's question about how to spread your learnings, we had an interesting comment you may have seen in the chat from Sal Tannenbaum, which was what you just referred to about the kind of gold standard that we see in epidemiology, randomized, double-blind, placebo-controlled testing. So, if the question is, what can mobility and transportation researchers learn from epidemiologists? Maybe one way to spread the gospel is to bring those two groups of people together. Would that be a constructive event, in your opinion?
Well, absolutely. But, we do have a difference between medical trials where you can impose those kinds of study designs versus earthquakes or a voluntary adoption of teleworking. No organization is going to randomly assign teleworking to some of its employees and not others, so as to get an unbiased estimate of the treatment effect on vehicle miles driven or even productivity. So I think, and of course, transportation is not unique with that problem. So I think it is, in many cases, a situation where the context doesn't lend itself to the gold standard approach, and we'll always have observational studies.
Yeah, it's a bit messier, if you will, than some of these carefully controlled experiments that we can do in medicine. Okay, so John Niles had a series of questions about the relationship between transit-oriented development and vehicle miles traveled. So as you think about those two, do you see, or is this just rampant with selection bias?
Yeah, I mean, I've studied a lot of residential self-selection, and the question there is, to what extent do people who want to free themselves from the automobile or be car light, at least, locate themselves into developments, residential locations that will permit them to travel less by car. So there's a pretty wide literature on that, and correcting for self-selection in a number of different ways. The results are also mixed. I got some papers or two with a previous PhD student where the quantitative estimates of the effects vary widely. And again, I think there'll just be context differences, differences in geographic context in which travel behavior variable you're measuring, whatever. But yeah, I think this technique is certainly applicable to that. And I think at the end of the day, Jinhua mentioned that we might be wrong even in directionality. And the example I just showed with teleworking is, I think, a case like that, where again, I got frustrated with all these cross-sectional studies claiming that teleworking was increasing travel. And I was like, I don't think so. And they haven't really controlled for selection. So, our kind of study more or less reversed the findings. But I think when it comes to residential self-selection, we're probably just talking about tinkering, with some kind of modest discount of what the uncontrolled for effect would be, if you know what I mean. But we don't know till we do it. And in any case, if policymakers are overestimating the impact of densifying or whatever it may be, it can be, there can be opportunity costs to doing that instead of something else, and that might have been more effective, or at least just not getting the desired or expected results.
So just in our last 2 minutes, Webb Faribault raised the question about sort of what are the biggest selection biases in transportation. You have shared with us many wonderful examples. Is there something that we didn't talk about that you'd like to share with the group? And let me just point out that Kara Kokelman from UT Austin jumped in and said, what about vehicle ownership? So I just wonder if you have any thoughts on that.
Yeah, I had vehicle ownership on one of the slides that I raced past, one of the many slides that I raced past. And, for sure, people who buy an alternative fuel vehicle or an all-electric vehicle, those who do it voluntarily are going to differ from those who are, nudged into it by financial incentives or ultimately regulations. And so, if we want to look at the impact on an all-electric car, on, I don't know, vehicle miles driven or whatever, again, don't project the effect that we see from early adopters onto later adopters. And similarly, I don't know, I couldn't pick a single one and say that's the most important one that we haven't talked about yet. I think, as I saw in the chat, assume they're out there unless you can demonstrate otherwise, because I think it's so pervasive. That's why I use the word insidious in the title. It's easy to not think about it, but when you start looking for them with at least these kinds of considerations in mind, I think you'll start seeing them a lot more places.
Yeah.
Great.
Super.
Yeah, the hour always feels so short. We're already it's the time now. So there's so many other phenomena we should discuss. And I really want to thank Professor Pat McTurn joining us today, talk about both of the methodology in the general way, but also the specific remote working example here. Everybody, please join me. Thank Pat for the presentation and conversation today.
Thank you very much.
Great. Yeah. Also thank Fred and Chandra for coming as well. Thanks. Have a good weekend. I'll see you next Friday.